Let's consider molecule A. Molecule A is optically active, and the reason why it's optically active because it has two chiral centers and it has a mirror image. If molecule A has all its chiral centers rotating in one direction, here it has all its chiral centers rotating counterclockwise. Then, if we look at its mirror image, the mirror image will have its chiral centers rotating in the other direction, which is R in this case. So A will be 50% as configuration, and B will be 50% R configuration. Let's say if we take molecule A and we combine it with B. So I'm not talking about A alone or B alone. A alone has a mirror image, which is B. So it is a pair of enantiomers. B has two chiral centers on the other end and has a mirror image, which is A. But if I take A and combine it with B, then in this case, my mixture will be 50% R, 50% S. And we call this racemic mixture. So taking A and combining it with B, what's going to happen to the plane of polarized light? I know A rotates the plane of polarized light to X direction. So let's say A rotates the plane of polarized light to the right, and it rotates it at 12 degrees. Its mirror image is supposed to rotate the plane of polarized light to the same extent, meaning the same angle, which is 12 degrees, but it's going to be in opposite direction. This is the rule for enantiomers in this case. However, if I have A, which is 50% S, and B, which is 50% R, and I want to combine those two together, so the plane of polarized light will rotate 12 degrees to the right and it will rotate 12 degrees to the left. So it's as if it did not rotate at all. If you combine the plus 12 and the negative 12, it will be a 0. So that is going to make the plane of polarized light for this mixture, A plus B, stand in its place and not do a rotation, either to the right nor to the left. So we call the mixture over here optically inactive mixture, and that mixture is called a racemic mixture. Earlier, we defined the term optically inactive, and we said that this term is used for molecules that cannot rotate the plane of polarized light. For a molecule not able to rotate the plane of polarized light, it should have either an achiral center, which means that a center that doesn't have four different groups. And if it has a center of four different groups, then you are able to draw a plane of symmetry, so you end up having a meso compound. These are the two cases where your compound is optically inactive. Now, the third case is whenever you have a racemic mixture. So once you draw your enantiomers and you see that one of them is 50% S, the other one is 50% R, both are, as we said, optically active, both. But if you combine them together, so both alone are optically active, but if you combine them together, then in this case, your mixture is going to be optically inactive, which is incapable of rotating the plane of polarized light. So these are the conditions where the sample is optically inactive. It either has no chiral center or it has more than one chiral center. In this case, we can draw a plane of symmetry, which is a meso compound now, or it's going to be a racemic mixture. These are the three cases where your molecule is not capable of rotating the plane of polarized light. Why do we care about racemic mixtures? Well, racemic mixtures have different physical properties and chemical properties compared to enantiomers. So if you have, for example, A alone has the same melting point as its mirror image. So mirror images, they have the same physical properties, but their racemic mixture does not. So melting point, in terms of melting point, the melting point of A is the same that of B. And the boiling point of A is the same that of B. And of course, vice versa in there. A and B which are enantiomers, they only differ in one thing only, which is the optical rotation, the rotation around the chiral center, because one rotates the plane of polarized light to the right, the other one rotates the plane of polarized light to the left. One has a chiral center which is clockwise, the other one has a chiral center which is counterclockwise. Now, if we go ahead and combine the two enantiomers together, then its physical properties are going to be completely different. So the melting point is going to be different. The boiling point is going to be different in this case. One of them is going to rotate the plane of polarized light to a certain extent in one direction, and the other one will rotate the plane of polarized light to the same extent but in another direction. So the sum of the rotation of the plane of polarized light is zero, and that is the definition for optical inactivity. There are two there are two equations that you are responsible for. The first one is enantiomeric excess. Now, these equations I want you to know how to use. I'll provide you those in the exam. Enantiomeric excess is the indication of optical purity, and it's a measure of how one enantiomer is present in excess with respect to the racemic mixture. So when I say, let's say, for example, if I have 90% enantiomeric excess in there, this means that one enantiomer is present 90% in excess to the racemic mixture. The racemic mixture is a total of 100. So what I have here left for the racemic mixture is 10% out of 100. So you look at your enantiomeric excess, and that is the excess of one enantiomer. So I have 90% excess of A. The remaining out of 100 is 10% racemic. Now I know that racemic is 5% A and 5% B. So now I can easily calculate how much is the percentage of A and how much is the percentage of B. So A here is 90 plus 5%, and B is going to be 5%. And I know now the percentage of my components, in this case, that make the racemic mixture. Another example, 60% enantiomeric excess. So I have 60% A, and the rest is going to be 40% racemic. Racemic here means that it's a combination of A and B. So 50-50. So 20% A, 20% B. I can combine A together, and now that means that I have 80% A and 20% B. Let's have more examples. Let's consider S-alanine. And we know that enantiomers, they do have physical properties that are similar. So if you have enantiomer A that has a certain melting point, then its mirror image is going to have the same melting point. So here, if I'm asking about the melting point of the mirror image of the S-alanine, which is R-alanine, then it's going to be the same as S isomer in there. So the melting point is going to be the same. How does the melting point of the racemic mixture differs? Yes, the melting point now is going to be different than its component enantiomers because now you are working with a racemic mixture. For the specific rotation of R-alanine, the specific rotation of R-alanine in there is going to be the opposite of the S-alanine. So if you are given the specific rotation, this is the alpha specific rotation. If you're given the specific rotation for the S isomer to be positive, then the specific rotation for the R isomer is going to be negative, but it's going to be the same angle. So it's going to be negative 8.5. Optical rotation of the racemic mixture of the S and the R, both of them, it's going to be 0 because this is a racemic mixture. In this case, 50% R, 50% S. Label each of the following as optically active or inactive. A solution of pure S-alanine, definitely it is optically active. It has a mirror image. Equal mixture, it is optically inactive because now it is a racemic mixture. A solution that contains 70% S and 25% R. Look, it is not 50-50% S and R. then it should be optically active in this case. A solution that contains 50% S, 50% R, then in this case, it's going to be optically inactive. The Another formula for the enantiomeric excess that takes into consideration the specific rotation of the mixture versus the pure enantiomer is this. So if you are given information now about the specific rotation, about the angle, here I do have a specific rotation of the pure molecule. So this is the pure enantiomer in there. Please include the signs whenever you are doing the calculation. And you have the specific rotation of the mixture, which is -16. You need to calculate the enantiomeric excess. So you divide them over each other, multiply by 100, and this is the enantiomeric excess. This is 50% EE. So we know that 50% EE means that 50% of A, and then another 50% is going to be for the mixture, for the racemic mixture. And that mixture has 25% A and 25% B. So I can easily calculate the percentage of A, which is 50 plus 25, that is 75% A, and the leftover is going to be 25% B. This way I can know exactly the components of the enantiomers in the mixture. If you have a Newman projection that has chiral centers and you're asked go ahead and find the configuration of the chiral centers in the Newman projection, then in this case you would need to change your Newman projection into a 3D structure or a fissure. I prefer to change it into a 3D structure and get the configuration. So we're going to go ahead, we know that Newman projection is around 2 carbons. So we're going to go ahead and draw the first carbon. So the first carbon has the OH, which is in front. So you draw it in front. And it has the hydrogen, which is behind. So you draw the hydrogen behind in there. And then you have your aldehyde. So this is the aldehyde, which is in plane. That is connected to the carbon at the back. And this is the carbon at the back. And it has the OH in plane pointing down like that. And then it has the alcohol group, which is pointing up, and the hydrogen, which is behind. So the moment I can change the Newman projection into a 3D, I can easily calculate or figure out the configuration of the chiral centers. Please don't do the configuration directly from the Newman. It's very hard. So change it into a 3D and do the configuration of your chiral centers in there. Remember that still the rules apply. So if your lowest priority group is not behind, you would need to switch the groups and you would need to find the configuration and then invert the configuration. This is every time we work with 3D molecules. So the most important question in this chapter is when I give you a series of molecules and I ask you, what is the relationship between them? How they are related? They can be the same, different enantiomers or diastereoisomers. So in order to figure out the relationship, you have to locate the chiral centers and calculate the configuration of the chiral centers. So if the configuration is the same, then the molecule is going to be identical. If the configurations are different by all chiral centers, then the molecules will be enantiomers. If they differ by some of its chiral centers, then they are going to be diastereoisomers. So as you can see, figuring out the configuration is very important. So let's have an example here. Redraw each Newman projection and determine the R and S configuration, and then determine how these molecules are related with each other. So each one of those, we're going to go ahead and change into a 3D molecule in there. Keep in mind that the molecules that are to the right of the Newman projection, they are always in front. The molecules that are to the left of the Newman projection, they are always behind in there. And then the rest of the molecules that lie on the vertical line, these are in plane. So the OH and the aldehyde, these are in plane. These two, they are in plane. So draw them in plane, please. And then draw the other stereochemistry of these two chiral centers. And there, I can easily see that I have a chiral center here and a chiral center there. We're going to do it for all the other molecules. Just move one element at a time. So for this chiral center here, I do have an oxygen that is connected to a carbon, and then a carbon and an oxygen here. So I know that the CHO, so a CHO is exactly the same as a C, which is a carbon double bond O and the hydrogen. And that is the same as a C connected to two oxygens and an oxygen connected to two carbons. And definitely I have a hydrogen on this carbon. The hydrogen is here. So this is the hydrogen there. So if I am looking at the priorities, definitely the OH over the oxygen is going to be priority number one. So that is going to be priority number one here. Now between the CHO and the CO, so here it's one CO, here it's a C which is connected to two O's. So this is going to be priority two, this is going to be priority three, and that is going to be priority four. And I am going by one, two, and three. I did not switch any groups because my lowest priority is at the back. So this is going to be an R configuration, and it stays an R configuration. For example, over here, the hydrogen is in front. Let's set our priorities. So OH is going to be priority one, the aldehyde is going to be priority two, and this guy is going to be priority three, and this one is going to be priority four. So what you're going to do over here is a switch one and four together. Let's draw it. And then one is going to be in front, and four is going to be behind. And then you have the two, and you have the three. This is an easier method if you don't have a molecular model. If you don't have a molecular model with you, you can easily switch those groups and make your lowest priority group behind. So, so in this case, you're going to go by 1, 2, and 3 over here. So this is going to be an R configuration. But remember what you did. You did the switch. So you switch, you do the configuration, and you invert the R. And now the R is going to be an S. So the first structure has its chiral centers. First one is on carbon number 2 and it's an R, and then on carbon number 3 and it's another R. So write down the configuration for the chiral centers to spot the difference in there. But on one condition, if you start numbering from one carbon, you guys keep numbering from that same carbon in there. So this is going to be 2, this is going to be 3, and this is going to be 4 again. And this is going to be 2R and 3R. So I can easily see that A and B are the same because they have the same chiral centers in there. And then for C, I have 2S and a 3S. So I can see that A and C, these are pair of enantiomers because their configuration is completely the opposite. And on carbon number 2, so this is, I'm starting from here 1, carbon number 2 is S, and carbon number 3 is an R, and I can see that B and D, these are diastereoisomers. Also, I have C and D. They are also diastereoisomers because they differ in one chiral center. Exam. So the relationship between the compounds, and again, you would need to locate your chiral center. Always locate your chiral center. Here I have one chiral center, and check your other component and see what happened to that chiral center in there. You should have a different connectivity of atoms. So I have a chiral center here. I do have a chiral center in there. Don't forget the hydrogen. So you have a hydrogen here. So this will end up having four different groups in there. If the bromine is in front, then definitely the hydrogen here is going to be behind. And here, of course, the hydrogen is going to be behind. Remember that every tetrahedral carbon needs to have two bonds in plane, one bond in front and the other one is behind. Do the configuration and see if they are the same, then it's going to be the same identical molecule. But again, on one condition, that you need to have same connectivity of atoms. So this is the first thing that you check first, that you have the same connectivity of atoms, and then you move along and do the configuration for the chiral center. Here, it's a different connectivity of atoms because this is a 1,4 and a 1,3 isomer. So these two are going to be constitutional isomers. Um, with this one over here, again, please do the configuration because with the configuration, you would know if you have enantiomers or diastereoisomers or identical. So for the configuration, I have two R's and two S. These are definitely enantiomers. For this one over here, these two, again, do the configuration for each one of these carbons, and you're going to end up having different configurations. So these are opposites. So again, they are enantiomers. As long as you are not able to draw a plane of symmetry, then your molecule is going to be optically active. For these two over here, again, do the configuration around this chiral center. So let's go ahead and do the configuration around this chiral center. You have your hydrogen, which is behind. So this is going to be group number 1. This is going to be group number 2. And that is going to be group number 3. And I am going by 1, 2, and 3, like that. So this is going to be an S configuration. Now for this one, I have my hydrogen, which is in front. So I need to switch at a certain point. I have a group 1, I have a group 2, and I have a group 3. So, and I'm going by, let's go ahead and just switch here. So we have, I'm going to switch the 1 with the 4. So now the 1 is going to be in front, the 4 is going to be behind, and then I'm going to keep the 2 and the 3 in plane. And I'm going by 1, 2, and 3, and this is an S configuration, but I switched the groups, so it's an actual R. So from S to R, these are a pair of enantiomers because they differ by one chiral center. For this one over here, if you have a cycle and you have components on the cycle, the first thing you check is the orientation of these compounds or these substituents with respect to each other. So if you have a trans and you're comparing it to trans, then there's a possibility for enantiomers. But if you have a trans and you're comparing it to a cis, then in this case, those are going to be diastereoisomers. So trans cis are always diastereoisomers. Again, here, trans and cis, these are diastereoisomers. Here I'm comparing two cis with respect to each other. So do the configuration, and these are enantiomers. They cannot be diastereoisomers. But a trans and the cis, they are diastereoisomers. Same thing, here, always check the connectivity. Here, this is a 1,4 disubstituted cyclohexane. This is also a 1,4 disubstituted cyclohexane, but it's a trans and this is cis. So these two are going to be diastereoisomers. Please work the problem sets posted. It's a one problem set, and it does have a lot of examples on what we have been talking about. Practice every single one of these problems before you go ahead and you do your assignment.